Okay, good evening, everybody. I'm extremely happy to stand here before you tonight because, first of all, I love the Royal Institution, but also I love talking to people who are apparently interested in what I hold very dear, namely gravitational waves and what I call nature's secrets. So what do I mean by that? What I mean is that we, as humankind, are extremely close to finding out some things about the universe that we have never understood or seen before. So it's my job tonight, in the next hour or so, to tell you all about that. And before I do so, I would like to, make a mental picture just for a moment. What do you think that the Nobel Prize winner of 2040 is going to look like? It's not me, I can tell you that, okay? But that person might actually be in the room right now. So without asking somebody specifically, sort of reading the room, many people might think, you know what, a Nobel Prize winner is probably somebody who has exploded hair, maybe a mustache, stands in front of a whiteboard scribbling calculations on there, which is true, those people do win Nobel Prizes. You might be thinking also about maybe some lady in a lab coat who is doing something with beakers, and that's true, those people also win Nobel Prizes. But when I think specifically about the Nobel Prize winner of 2040, I'm very much more thinking about a person who looks like this. And maybe it's this person. And maybe still it's one of these geniuses. You might notice that none of these Nobel Prize winners of 2040 have frizzy exploding hair and stand in front of a whiteboard. Okay, they're not even that old. They're probably somewhere between 10 and 20 years old. And the reason for that is because we're going to build a machine, humankind together. And this machine is the one that's going to look at the universe, but that machine will only be ready in a decade and a half or so. That's just about the moment when these people are going to be Nobel Prize age, okay? So it might very well be that these people don't even know yet that they're going to win the Nobel Prize because they're still in high school, secondary education. Who thinks about Nobel Prizes at that age, okay? I certainly didn't. So how do I know then that they're going to win the Nobel Prize? Well, again, it's because of experiments coming our way. Here's one of them, the Einstein Telescope. So what is the Einstein Telescope? Well, as you can notice from the picture behind me, the machine doesn't yet exist. It's not a photograph. It's an artist's impression. The machine has to be constructed yet, but we are working on this. We have been working on this for the last decade, 2 decades or so, and that machine will start its construction in 2 years from now, and will be ready about 2035. Again, that's close to Nobel Prize age of these people that we just looked at. Okay, so in brief, we will talk about this much more later on in the presentation. What will the machine do? Well, it's going to take a couple of laser beams, shoot them over a 10-kilometer range in a triangle, deep on the ground, and using those laser beams, in a way we will discuss later in the talk, they are going to measure gravitational waves. And gravitational waves are exactly the key messengers about the big secrets of the universe that we as humans have never seen before. So it's going to be quite exciting. Okay, so indeed, my name is Gideon Koekoek. I'm an associate professor of theoretical physics at Maastricht University. If people are not in the know, that's all the way in the southern tip of the Netherlands, and I work in the Einstein Telescope Consortium. But at the same time, I'm also highly interested in making sure that the younger generation knows about this stuff, and that they know that they're welcome to join us in this effort. So that's what I'm going to do tonight as well. Let's start with what exactly do I mean when I say gravitational wave? Well, here's a video. What you see in this video here are 2 stars. They're orbiting each other, and they collided. They were black holes. And as they were orbiting and colliding, there was this sort of greenish ripple that's now floating out of it. And it makes space dance and wobble, and that wobbling, dancing space is now moving through the universe with the speed of light. And yet it still takes a few billion years, but at some point they will arrive on Earth. And that's what you're seeing right now. The Earth is now being washed over by these gravitational waves. This is a highly exaggerated effect that you see here. Okay? We will talk about that the effect is ridiculously small. In fact, it's so small that probably right now hundreds of gravitational waves are washing over us without ever any of us noticing at this point. They're just so ridiculously small. They're much smaller than atoms still. So we have to go into work really hard to make them measurable. And that is, of course, exactly what the Einstein Telescope is going to do for us. So I'm going to walk you through all of this, and I'm going to do this in 3 questions. First of all, I showed you gravitational waves apparently make the universe wobble, but what is space to begin with, and how can space wobble? That's going to be my first question for tonight. Second question is, okay, but if we now know that space can wobble, how can you use it to see, as I promised, things that are invisible? And then finally, after we are going to wrap up, I'm going to tell you how does the Einstein Telescope do it, and what can we learn about the universe. So, that's the plan. Here's the danger, though. If you're going to ask a physicist, please explain some physics to me, the first thing they do is bring out a whiteboard and start scribbling mathematics, okay? That's not my plan for tonight, because mathematics are just a cover-up for a deeper understanding. And that deeper understanding typically isn't really that difficult. So I'm going to try to explain this to you, not using any mathematics, simply by, well, what is nature really doing? And here's the nice thing about nature. It has rules, but it has only few rules. So nature has a tendency to repeat itself over and over again. And that's a good thing if you try to understand, because that means if you have understood nature here, and you don't quite understand it there, the only thing you have to do is realize what is the underlying rule, and is it shared between those two phenomena? And the answer is very often yes. So I'm going to point it out as we go along. And by using the fact that nature repeats itself, that's going to get us a whole long way to understand how all of this works. So let's get started. What is space and how can it wobble? That was my first question. Well, space, if I ask somebody what space is, they're probably thinking about outer space, as in, where the stars and the planets and the galaxies live. Certainly true, outer space is indeed very spacious. There's a lot of space there, yes? But when you ask a physicist what space means, they simply mean distance. How many meters, kilometers, light years are there between point A and point B? So in this picture, what you see, for instance, is, well, there's a galaxy in the lower left corner. And all the way in the upper right corner, you might have a black hole in red. And there's distance in between. Could be a few light years, maybe a few million light years, but there's distance. That's what I'm going to mean when I mean space. It need not be big space, a big amount. For instance, you and I have a spatial distance of a few meters. That's also space. It's also not going to matter for my story whether that space is filled with something, like it is in this room, it's filled with air, or that space itself is empty, as in outer space it is. So that's what I'm going to mean with space. Now, here's what Einstein realized. We're talking about 1915 to 1916. He realized that space is elastic. What do we mean by space is elastic? It means that it can be stretched out and stretched in. Can I use you as for a demonstration? There we go. I'm going to make myself some distance between you and me. Can I ask your name? Hi, Arthur. It's Gideon. There we go. So there's, 2-3 meters between the two of us now? Yes? So there's space. That's what this slinky, this spring, is depicting. Now, this space can be made bigger. The only thing you have to do is just walk backwards for a little bit. Or I can make it smaller, just don't let go, and walk towards you. Then I can make the 2.5 meters, 3 meters, I can make it bigger and smaller. That's fine. But now I'm doing the work. And you could do the work too, right? You walk back and forth. But Einstein figured out, wait a minute, space itself can do it. Space in between us, without Arthur moving or myself moving, space itself can stretch out, and the two of us have no choice but to move along with space. In or out, so on and so forth. That's what Einstein figured out. Well, that sounds very strange, right? You probably have never felt this before, seen this before. Again, it's because the effect is ridiculously small. But it does come with a nice advantage. And for that, Arthur, I'm going to ask you to close your eyes for a bit. Can somebody check that he's not peeking? Okay. Because, Arthur, you cannot see me right now, right? Good. Okay, so suppose Arthur is sitting over there, and I'm on this side of space, but I start to dance around for a little bit. Arthur, can you tell that I'm dancing? All right. You can feel it, right? Here's the good thing. You can open your eyes again. Thank you very much. Can I have an applause for Arthur, please? Thank you. So what this effect is showing us that if space indeed is elastic, that means you can make it wobble. And if you can make it wobble, then that means that people like Arthur can actually measure that I'm around. If you're really good at maths, I don't know if you are, but okay. Me neither, but everybody's fooled. So that means that if you then can calculate the amount of wobbles, you can calculate back how many kilograms I have, how many meters I was away from you, how my little dance was going, all these things. So it gives us a means to look at the universe in a way that doesn't require light. And that's what I meant when I started, that I said that you can use gravitational waves to look at things that are invisible. Literally invisible, because you were not able to see me, right? That's the promise that gravitational waves hold. Here is what Einstein wrote down for us to calculate gravitational waves. It's a formula. And formulas are complicated. This one doesn't look too complicated. That's because the symbols in it are chosen not to make it look complicated. If you would write this out, it takes about 5 slides. Okay? Yeah, trust me, this is my job. I have to do this every single day, work with these equations. This is where I can use a little trick. Remember that I said nature likes to repeat itself? So if maybe we can replace the difficult formula by some other place in nature that plays by the same rules, we can understand it a little bit better. And we just have to look for the right place to look. And here it is. We simply have to ask ourselves the question, how do things fall? It sounds almost like a silly question. If I trip over my shoes, I'm going to fall on the floor. Why? Gravity. Gravity is going to pull me down. Sure. But Newton, your famous countryman, found out 300 plus years ago that gravity is a little bit more than just things falling towards the ground. Because it's not just the Earth that pulls on you, it's every single thing in the universe that has mass, that has kilograms. Me having kilograms and pulling on you right now, I cannot help it. You cannot help it either. And every single one of you with your kilograms is pulling on everybody else. This effect, again, is very small because things like to drop towards the thing that pulls the most. So we have to look for the thing that has the most kilograms of all close by. Well, that's the whole planet itself. Yes? So this is why, in practice, people might think that, well, gravity is just the Earth pulling on you. No, every single thing with kilograms is pulling on everything else. Good. Okay. Now, let's look at the following situation. This is a problem that was solved already by Newton 300 years ago. And using this problem and its solution and adding an extra layer to it, we can understand why space is elastic and therefore why we can make it wobble and let Arthur know about my existence without him seeing me. So let's go 300 years back in time and see what Newton looked at. One of the questions that Newton was trying to solve was, well, if there's gravity between any two sets of kilos, for instance, the planet Earth and the moon, then sure, okay, then the moon is orbiting the Earth, but why doesn't it fall down? Why doesn't it clash into each other, right? I mean, if the Earth is pulling, why doesn't it drop down? And again, this problem was solved. This is how Newton and his contemporaries did it. Newton said, well, listen, there is gravity between Earth and moon. That gravity here is depicted by the blue arrow. So it is being pulled inward. Again, question remains, why doesn't it drop down then? Then Newton realized, wait a minute, things really love to go into a straight line with constant velocity. That's what we call the inertia of an object. If you push something, it tries to move straight forward without being pushed or pulled in any direction. Inertia. So that would be this arrow in dark blue that you see right now. But then the following happens. Listen, if I'm running in that direction, that's my inertia, the dark blue arrow, and somebody over there is pulling on my arm, that's gravity, I won't go in that direction. I also won't go in that direction. I will go through the middle. I will be pushed to the side. That's the orange arrow that you see here. And the moon then ends up at this new position over there. But because nature likes to repeat itself, the same trick will happen at this new position. There's an arrow, gravity, trying to pull it in towards the Earth. It still wants to go into a straight line. It's inertia, but now it's slightly slanted, and it will again go through the middle, orange arrow. And if you keep this up for every second, you get a nice circular orbit of the moon around the Earth. This is how Newton solved the question, why doesn't the moon drop on the Earth despite their strong pulling towards each other? It's this interplay between inertia and gravity. Here's an extra layer that I'm going to put on top of it. This is not Newton's. This is our present understanding of these things. Look what I'm going to do. Here's some train tracks. As the moon is orbiting the Earth, it's almost as if this interplay between inertia and gravity makes the moon attached to some invisible train tracks that's telling the moon where to go at any moment. Move, 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 move. Okay. Here's a question, though. What if we're going to make the moon twice as heavy? Something like this. Question. Will the moon stick to those train tracks? Or will the moon train derail? You might be tempted to think, well, it will derail, because obviously it's the extra strong pull that they have because you've upped the mass of one of the two objects, so yeah, how can it ever stick to the train tracks? But here's the cool thing, it will actually stick to the exact same train tracks. In fact, you might make the moon 10 times as heavy. You can also make it 10 times as small. It will always stick to the exact same train tracks, and that's a good thing. It tells us that the train tracks, if you will, are universal. They're baked into space itself. It has nothing to do with the moon, be it 10 times as big or 10 times as small. You can replace the moon by me, and I will move along the same train tracks. Okay, but how? How do we know that this is the case? I mean, it sounds strange, because I was telling you, well, it pulls 10 times as big now, right? 10 times as many mass. Well, I think the best thing we can do is to do this by demonstration. So what I have here is a small amount of mass. And sir, I happen to be looking at you. Would you mind being part of this demonstration? Sure. And can I ask you to come in as well? Can I have your names? Alex. Hi. And hey, welcome both of you. Can I have an applause for our volunteers? Okay, so I have a certain amount of mass here. It's a few hundred grams. Would you mind holding this for a moment? Okay. And would you mind holding it up so everybody can see? There we go. Okay. Yeah, okay. This is also mass. It's about 10 kilograms, I think a little bit more. So it's about 100 times more than you're holding right now. That's my job. That's your job, yes, exactly. There we go. Okay, well, the rest of us, let's take a moment to look at the strains on their faces. Well, you're clearly not having a lot of trouble. How are you doing? Okay. Exactly. So this is, of course, what gravity means, right? I mean, more kilos means more pulling, and that's what you feel with your muscles right now. I'll take it off of you for a moment. If you can keep standing here for a second, I'll also take this off of you now. Okay, this is, again, just a repeat of the question. If you make mass 10 times as big, well, you have to strain a lot more, so why doesn't it drop down the moon? Well, here's my little demonstration. Would you mind giving it a little kick? A little harder. That worked out. Okay, good.
I'll do my best.
Don't kick too hard, though.
No, of course. Shall I?
I don't know, you might break a toe. Let's not do it, okay? Okay, right now that's all that I want from you. Ladies and gentlemen, it's conventional that after we've had some volunteers that you're going to get an applause, but we're going to hold your applause for a little bit. It will come later in the presentation, okay? So if we can just invite you back, well, let's do a very small applause for them, okay? Yeah, okay, there we go. Thanks. Okay, oh. Okay, well, what was this demonstration all about? Well, one of them was that we could really test that a big amount of mass, more kilograms, gets pulled down a lot more than the not so big amount of mass. In the meantime, can I ask you to set up the pendulum? But there was something else that we saw. The reason that you really didn't want to kick this big amount of mass over here, and I warned you against it, is because mass does something else as well. Mass isn't just how much gravity is trying to pull things down. What mass is also telling you is that things don't like to be put into motion. Agreed? This is why you would probably have broken your toe if you kicked it too much. This is one of the great discoveries by Newton. Newton found that mass, the number that tells you how many kilograms you have, in my case that's 90, if you believe it or not, that the 90 kilograms has two meanings. On the one hand, it tells you how much gravity wants to speed it down if you let it go. That's why you have to work so hard to keep the 100 or the 10 kilograms up. But at the same time, the 90 kilograms is also a measure of things not wanting to get into motion, that things really don't want to be sped up very much. So on the one hand, mass means wants to be sped up by gravity. On the other hand, it says, well, actually, I don't want to be sped up at all. I'm going to break your toe if you try to kick me. Yes? And those two effects, the fact that nature repeats itself, that it uses the same number twice, is exactly canceling. So if you now look at the moon again, and you would up the moon's mass by a factor of 10 or so, as I was doing in my picture before, it's certainly true that it wants to go down towards the Earth a lot more, but at the same time, this other meaning of mass tells you that it really doesn't want to start moving in that direction at all. And it cancels out. This is why those train tracks that I was talking about are what I would like to call universal. They don't care about how big the moon is, or whether I'm in that orbit, or whether a cheese sandwich is in that orbit. Every single object will follow the exact same train tracks. Mind you, just as real train tracks. If you go to the London Underground, and you remove a train cart from it, and put a completely different train cart on it, nobody is going to be surprised that that new train cart is going to take the exact same corners at the exact same place, right? Because, hey, it's not the cart that determines where it goes, it's the train track. The train track is universal. It doesn't care about which cart. That's the same with mass. And we can demonstrate this right now. Because look, I have a very heavy mass here. I believe it's about 10 or 20 kilos. This is about 1. If my story is correct, and Newton is correct, then that means these two, once I let them go and swing, will follow the exact same path. They will follow the exact same invisible train track. So let's see if it goes. Don't worry. And they follow the exact same path. If you squint, you can actually see the train track. Right? It's this curve that they're trying, both of them trying to follow. There you go. So, with this demonstration, you can see that the train track story is actually really, really, really true. Now, Newton never quite realized it to this point, but that's the point that we are going to make. The fact, again, that mass is used twice by nature. Nature likes to repeat itself, tells you that space is filled with invisible train tracks. And it doesn't care what is moving on those train tracks, it will make everything follow the exact same path. So, I made an animation where you can see that happen. You see the moon, the Earth there, and look at those white lines that I drew around them. Those are the invisible train tracks. Of course, I made them visible by my animation, but this is what nature really, really, really does. It makes space curved. The train tracks are baked into space itself. And that's what physicists mean when they say that space is curved. There's a curved space. That's a deep understanding. Newton never made this connection. That's our insight a few hundred years later. Okay? And this might sound very, very odd to you, because space is just pure emptiness, right? Could also be outer space. And how can outer space have any properties, let alone be curved? How would you be able to tell? Well, let's first ask ourselves, how can you tell that things are curved? Well, one very good way is to look at things from the outside. If you want to know that the Earth is not flat but is curved, the only thing you have to do is take a rocket, blast off, look at it from a distance and see, you know what? That's pretty curved. I know there's still people these days that's different opinion on the matter. Okay, but there you go. You can just blast off, look at it from the outside. But first of all, Earth is a tangible object. You can look at it. It's hard to look at empty space. So how can you tell that empty space is curved? That's one. Secondly, the curvature that we now concluded isn't part of a surface where you can blast off from. It's part of this space around us in all directions. I don't have any direction to go into with my rocket to look at it from the outside. So how could I possibly tell that empty space indeed is curved if I cannot leave space to look at it from the outside? And I asked two of my students if they could make this understandable for us. So they made this video for me. Here's two students. Left is Nelson, right is Kai. And Kai and Nelson are dressed up as Greek philosophers. Greek philosophers, in the ancient days, all of them had big beards apparently, they wore togas, so they dress up as Greek philosophers. And Nelson and Kai are going to demonstrate how can you tell that space is curved if you're not allowed to leave space. And note, the only thing they're going to do is draw a triangle. They start with a triangle drawn on the floor. Just any everyday triangle that you learn about in high school. And they're going to strip the triangle off of the floor and reattach it on this curved space, in this case a globe. Lo and behold, and as good Greek philosophers, they end up stroking their beards, wondering what to do with this revelation. What they're showing us is the following. You can tell the non-flatness of a space simply by drawing a triangle. Draw a triangle on a flat space. That was the floor in the demonstration. And all your regular rules about flat space work there. Pythagorean theorem, the sum of the angles is 180 degrees, so on and so forth. If you draw that same triangle on a curved space, in this case it was a globe, you can actually tell that the rules of triangles don't work anymore. They're broken. That's a good thing. That means we can tell that space is curved, not by blasting off and looking at it from the outside, simply by drawing a triangle. You can tell that Earth is a sphere if you would draw a triangle on it and try to do Pythagorean theorem. Or maybe if you add the sum of the angles and see that it's not 180 degrees. You have to draw a pretty big triangle to make it visible, but it's there. But note there's something else going on as well. Look at the part of the triangle sticking out all the way to the right. Do you see that actually sticks out? That's what they showed us, Kai and Nelson, in the video. It's stretched. Because we went from a flat to a curved space, distance stretched out. That realization, us going from flat to curved and therefore space had to stretch, that's why space is elastic. That, with our current day understanding, is why Einstein and his contemporaries came up with the idea that space indeed is stretchable. And all of this, at the end, simply came from the idea that nature likes to repeat itself, that it uses the 90 kilos for two purposes. And all of this follows. By the way, Einstein also found out that time is elastic. You can stretch time. I'm not going to need it for my story. If you want to know more about that, ask me later. We have a Q&A session coming up. For my story, I just need the stretchiness of space. So, let's look at a couple of examples. If this is true, then that means that everything that tries to move through that space that is curved has no choice but to follow the invisible train tracks. And that includes light. Light is also a train that tries to run on the track, but the track tells it where it has to go. So one thing that you can measure, for instance, is, if this theory is true, that a light ray that tries to graze around the sun has to follow the train track and gets a curve. And that's a measurable effect. In fact, it was measured by one of your very famous countrymen, Sir Arthur Eddington, who measured this in 1919. Lo and behold, the effect was exactly as Einstein predicted. So the effect is not a fairy tale, it's really there. But there's a second one. And Arthur, you and I just had the demonstration that space could be stretching out, right? And of course, I did it now, but space itself can do this. So Einstein and later contemporaries also figured out, well, if space is stretchable, that also means that universes should stretch out. Space between the two of us is stretching out, but the space between you and any other person in the room is also stretching out. So if this is true, then that means if you look at the stars and the galaxies, all of them should, first of all, be moving away from us, because the space between us is stretching, but also be moving away from each other. And that too was measured. This is 1929. What you see in the right panel. This was measured by Edwin Hubble. And this, again, was confirmation that Einstein's theory of stretched spaces really is true. By the way, we're 100 years later now. We haven't found a single refutation by measurement of this theory. This is absolutely true. This is great. And all of this, again, we got simply by looking at what masses do. So, let's recap. What did we see? Stretch space, very difficult. Use the fact that nature repeats itself. Use the fact that nature uses the number that we call mass twice for two effects, and all of that led immediately to the idea that space is elastic. And that's good, because that means we can teach it to high school children, including our future Nobel Prize winner in 2040. That's a good thing. Now, we also did the experiment where I wobbled space, and you will be able to tell that I'm around even if you cannot see me. So that allows us to look at the universe, at things that are invisible. So let's take a picture of the universe. Here it is. There's all kinds of interesting stuff. We don't have to focus on every single thing. I will tell you, though, it's a timeline. If I'm standing over here, all the way to your left, that's the start of the universe. Timeline all the way over here, go to the right. I find myself 13.8 billion years later. And within that time, all kinds of beautiful things happened. Stars started to shine, galaxies came up. We came up at some point, the Earth and the people on it, so on and so forth. And all of this was measured by using light telescopes. Right? Put a telescope, point it towards the sky, measure light, and you should be able to see what happened in the universe. Mind you, this is a way to look at the past. Because if somewhere over here there was a star sending out a flash of light, that light has to travel from me, from its location, to me standing over here in the present, and that takes a few billion years. So by the time I'm catching that light, I get a snapshot of what the star looked like a few million years back. And having done so as humankind in the last couple of hundred years, we have been able to fill up the history book of the universe, to take snapshots, so we know pretty well what went on in the last 13.8 billion years. But there's also stuff that is invisible. I'm going to highlight two of them. One of them is, sure, we can look at the universe using light, but we also notice you can look at the universe by looking how much it curves. Those are two separate measurements. And from the curvature measurement, you can calculate how much kilograms there should be in the universe. From the light perspective, you can measure, well, how much stars are there, things that send out light. Those numbers do not match up at all. Think about this. This room, Royal Institution, is filled with all of us. We're all consist of particles and kilograms and so on and so forth. If you would measure just by sight how many kilograms we have over here, we only add up to about 4% of the contents of this room. I'm not talking about air. We've taken that into account. There's 96% missing. And we can tell by the curvature of space that that stuff is there, but it doesn't send out light. Nobody knows what that is. This is what we call well, there's a slight distinction, but there's dark matter and dark energy. Stuff in the universe that apparently is dark because it doesn't send out light. We cannot see it, but we can tell its curvature, the invisible train tracks that it makes. Nobody knows what that is. Could be our Nobel Prize winner in 2040, who's going to figure that one out. There's something else that cannot be seen. If you go all the way to the left of that picture, so that's very close to the start of the universe, you can see this slab that's in blue and greenish or so. That's the first light that started to shine in the universe. No light was ever seen before. I will tell you in a moment why that's true. Why is it that in the very early universe, there was no light? And when I say very early, I mean about 400,000 years after Big Bang. Now, to us, that's a large time. For the universe, 13.8, very small. But that's a sucky situation for us physicists. Because this is where the cool stuff happened. This is where the universe sprung into existence. And it's exactly that part that never sent out any light. So there's no point in trying to build a big light telescope to try to catch that light from the early universe. It wasn't there. It was never sent out. So wouldn't it be nice if we had a way to look at the universe without light? Arthur, do you remember a nice way of doing that? Okay, can we have a demonstration of that, please? We're going to demonstrate this right here on the spot. By the way, this is also the moment, as Dan said at the beginning, where we're going to have a stroboscope. So if you happen to be sensitive to that, you might want to avert your eyes. It only takes a few seconds. So the team is now bringing in a piece of space. And as we discussed before, space is stretchable. There you go. In a moment, I'm going to make myself a gravitational wave using this drill. Now, usually on a drill, you have a drill. Not this time. What we have is two little wheels. Each of these wheels simply means kilograms. Maybe a star, maybe a black hole. You know what happens if I place one of these wheels on the stretchable material? We spoke about it. Then you're going to make local curvature. You're going to introduce invisible train tracks. Each does that. Shall we try? Now, excuse me, I should have warned you. It scared me too. I'm going to make those two stars, black holes, what you will, those two sets of kilograms rotate around each other. And let's see what we're going to do. Please switch it on if you can. And that was that. Did you all see this? Thanks, team. So, can we have an applause for a beautiful stage team because they're so good at this? Jin and Judith. Yeah, so this is what we saw in the very first video that I showed you, that if things in the universe are dancing around each other, space around it will dance as well. Even if you cannot see them, like we cannot see really black holes. So the only thing we have to do is stand on the side, wait for this little dance to come to us. We start to bob along. We have no choice in the matter. We're part of space. And we start to dance along. By the way, in case it didn't work, we had a pre-recorded video. Worked just fine. So we're going to skip this one. And that gives us, again, one of these moments where I can say nature really likes to repeat itself. If we're all going to be very silent for a moment. Well, then we cannot hear anything. Yes, that's what silent means. Air, when it's stationary, in this room right now, cannot be heard. But if I make air wobble, I'm doing this now with my vocal cords, you can actually hear me. Wobbly air can be heard, stationary air cannot. In very much the same way, nature repeats itself. It does the same with what we call the electromagnetic field. Faraday, a great scientist that was affiliated with this institution 200 years back or so. Faraday was one of the people who found this out. We have this thing called the electromagnetic field. It's what tells magnets that they should be attracting each other. The invisible train tracks of magnets, so to say. Those electromagnetic fields cannot be seen if they're stationary. But if you make them wobble, they become light. That's what light is. It's the wobbling of the electromagnetic field. So, stationary air cannot be heard. Wobbly air can be heard. Stationary electromagnetic fields cannot be seen. Wobbly electromagnetic fields can be seen. That's what we call light. We now have a third instrument. Nature repeats itself. You can really, in a very difficult way, just not see a stationary space. But when space starts to wobble, as we were demonstrating before, you can. And there's all kinds of interesting properties. For instance, if you stretch out light, it goes from what we call the color blue all the way to the color red. If you stretch out a wobbly piece of air, sound, you're going to go from a high pitch towards a low pitch. Now, if you stretch out the gravitational wave, the same thing will happen. We don't have a name for it yet, okay? But the same thing will happen. And this is the way that we can also understand how it is that we cannot see beyond that first 400,000 years, this slab that we looked at before, the first light that came out. Because I told you, with gravitational waves, we can actually pierce through it. We don't have to look at light, we can also look at the wobbly space. And the wobbly space is actually before the 400,000 years. So if we can measure those gravitational waves, we will be able to measure what happened in the first 400,000 years of the universe, where all the biggest secrets lie at this moment. So that's exciting. What I have not told you yet is why we cannot see through that first slab of light. Why is it that it took 400,000 years for the universe to give us light? We have another demonstration coming up. This one contains fire and chemicals. All right, let's see what we have here. I'm going to turn on some fire. There we go. There we go. Fire. The next thing I'm going to do is I'm going to spray some chemicals in it. And sir, without telling me, can you say what it says? Okay. Was it sodium? It was. Great. Then let's do another one. Okay. Sure, absolutely. There we go. Thanks, Jim. Let's go over here. Sir. There we go. Can you say what it says? Or don't tell me. Yeah? Got it? Huh. Potassium. Yes, there we go. Let's do one more. I'm thinking copper. Can somebody verify? Yeah, I got a thumbs up. Okay, great. So, what we saw here is something very special about the nature of atoms. You see, atoms, thanks guys, atoms have a special property. Every type of atom comes with their own color code. Copper really likes green. And sodium really likes yellow. So on and so forth. Why this is true, that's a nuance that's not my topic for tonight. It has something to do with quantum mechanics. But that's true. Every single type of atom has their own color code. So if I would have, for instance, a gas of copper here, and I would try to shoot a light through it, it really loves green light, as you just saw before. That's why I could tell, without reading the label, which one was which. I know the color codes by heart. Not all of them, by the way, but these I could. Okay? Yeah, there's about 106-ish elements. I don't have the time to memorize these things. So every atom has their own color code. So if I have a cloud of copper here and I shoot light through it, what this copper says is, you know what? I really like that green part. I'm going to keep it with me. The other part's going to fly through. Same thing with sodium. If I have a gas of sodium over here and I'm going to shoot light through it, then the sodium says, you know what, that yellow stuff, that's for me. I'm going to keep it with me. Well, if it's going to be kept with the gas, it's not reaching our eyes. Yes? Let's go to the start of the universe. The start of the universe was filled, those 400,000 years after Big Bang, was filled with hydrogen. And hydrogen has its own favorite colors. That's the one that you see now on the screen behind me. So what does hydrogen like? Which colors does it like to keep with it? Well, it likes purple for a bit. There's this particular type of blue that it likes, and it also likes red. Okay, good. Can I have my string? So, if the universe starts, everything was very compact because the universe had not stretched out very much. And if the universe has not stretched out any much, that means all the color waves in it were trapped as well. And trapped waves look very, very, very blue. That's good, because hydrogen likes blue. It likes purple. So what did hydrogen do? It kept that light with it. Well, here is the universe when it was very small still. Let's hear what it sounds like. Its pitch, its color, if you will. Okay, particular pitch. Let's make the universe expand. Let's make it stretch out, as we know that it does. Because the stretchability of nature allows this to happen, and we saw by measurement 1929 that this is what happens. This is the universe a few 100,000 years, million years later. It's been stretched out. Let's listen what it sounds like now. That's a much lower pitch. That means, there we go, thanks guys. In colors, then that means that the universe might have started with blue color, but as it stretched out, the color became red, and more red, and more red still. And there is a point, as we can see over there, that if you stretch it out enough, it becomes red and more red and more red. At some point, hydrogen says, you know what, I don't like this color anymore. I'm going to let it go. And that's that moment after 400,000 years after Big Bang. The universe had stretched out so much that the light stretched out as well, making all the colors too red for hydrogen to keep it with it, and then it let it go. And we can calculate when it happened, 400,000 years after Big Bang. Okay, so all of that is good. If this sounds familiar to you, that's because it's very much the same effect that you have when it starts raining. This has nothing to do with space. It has nothing to do with elasticity. It's nothing to do with Einstein. It has simply to do with clouds. Have you noticed that it typically starts to rain at the moment that it gets cold? Yes? It's because clouds float around in the sky. Clouds take up water droplets, and they keep it with them. But when it gets too cold, at some point the clouds say, you know what? I don't like these water droplets anymore. I'm going to let them go. That's what rain is. So let's demonstrate this right here. I actually have here air. I'm going to make sure it's nicely saturated, and now I'm going to make myself a cloud. How? Well, I'm going to set the water on fire for a bit. I'm going to make some steam. So I have now air in here that is highly saturated with water. I'm going to make myself a nice cloud. There we go. You cannot really see the cloud because it's relatively small. If you're very up close, you can see it. Now here's the thing. If I'm going to press the bottle now, pressing the bottle is going to make the temperature go up. That's what pressing does. If you press something really hard, the temperature goes up. So right now, there we go. I have a warm cloud. Warm clouds like to keep the droplets with them. But if I let them go, did you see that? This flash of droplets, because when I let go, I made the temperature go down. Let's do it one more time. There we go. Nice warm cloud and cold cloud. And there we go. It let go of all the droplets. And the exact same thing happened. Again, nature likes to repeat itself. Happened in the early universe. The universe started with hydrogen. It was very warm. Blue light, this very warm light. The universe stretched out. At some point, it became too cold. And all of a sudden, it started to rain light back into the universe. And that was that slab of light that we saw, the first 400,000 years of the Big Bang that you see in the picture. So that's why we cannot look at the start of the universe. The droplets were kept in the hydrogen gas, but at some point they came out. But if we want to peer through that slab, what we have to do is get a gravitational wave. Okay, so here's a few examples of things that are invisible that you can now actually make visible with gravitational waves. They carry snapshots about the universe. What they do is they can even pierce through that starting point of the universe, 400,000 years, and in addition to that, you can look at all that invisible stuff, the 96%. And again, all of this is something that really goes well with what you already know. For instance, rain. So that makes it perfectly capable to teach our Nobel Prize winners of 2040. Okay, moving on. We had a third question lined up, namely, okay, but how are we going to measure these gravitational waves? Well, they're extremely small. I mentioned this at the beginning. A gravitational wave is, well, if I pluck one of my hairs out and I look at the thickness of it, and I chop it up into 1 million pieces, and then I take one of those pieces and I chop it up another 10,000 times, that's about as big as a gravitational wave is, okay? So you better measure really, really well. But we have a trick to do this. We use light. Here's what we do. We're going to take a laser beam. We're going to shoot it back and forth between a few mirrors. And if you shoot a laser beam from me to the other side of the room, it will bounce back. And by measuring how long it takes for the light to bounce back and forth, I can tell how far away the room is. So I can do a length measurement using light, laser light. We use 2 of them to make the effect more pronounced. So that's what we do. So that's very nice. Nature, again, repeats itself. We can use the waviness, so to say, of light to measure how far away things are. And light, laser light, is extremely sensitive to very small distances, even as small as this very small thickness of my hair. So I have the demonstration set up. Can we dim the house lights, please? I have one of those apparatus right here. These are the 2 laser lights that we just saw, put on top of each other. And you can see this beautiful pattern over here. All of this is bolted to a metal slab. Now, I don't have to tell you that metal is very hard to curve, right? You have to be really strong to make it curve. But I'm simply going to press my metal slab now with my little pinky finger. Look at the pattern. Do you see how it changes? The house lights can go back on, please. So I was able, literally use my pinky, when I pressed the metal slab over here, it curved ever so slightly. And even though it's a ridiculously small effect, it's much smaller than even a millimeter, I was perfectly able to see this with the pattern that I saw on screen. So this is how we measure gravitational waves. If we take 2 of these mirrors and we let the gravitational wave fly by and the Earth will wobble ever so slightly, the laser light pattern, as we saw here, will reveal it. And we notice this trick works because we have been doing it for about 10 years now. The first gravitational wave was measured in 2015. And this is what it should have looked like if 2 stars were orbiting and made the universe dance. This is what it should have looked like. This is what it looked like when the measurement was done using exactly one of these. The machine had to be really big. I mean, you can see them in the United States. They're about 4 kilometers each, right? But it's the same effect. And there's lots of technology to make it work. Well, this was worthy of a Nobel Prize in 2017, the first measurement of a gravitational wave. Since then, we have measured about 100 of them. So, roughly speaking, we measure about 100 gravitational waves every 10 years. It's hard work. The effect is still very small, even if we use light. So we have to work hard to do this. And that in total gives us, well, all these blue dots is one of these measured gravitational waves. We have 4 of these detectors in the world right now. We have the 2 in the United States. We have 1 in Italy and 1 in Japan. And all of them form a network and they measure this. But, and again, we can learn all kinds of interesting things about this. Now, let's make a little bit audible what I mean that we measure these things, but we can measure them a lot better. Let me clap. Just do a little slow clap by myself. One clap. That's one gravitational wave measurement. I wait a week. Another clap. I wait another week. Another measurement. That's about how quickly these things measure gravitational waves. The effect, again, is really small. What we want is to turn this one clap per week, this slow clap, into one big thunderous applause that we can listen at the universe. Gentlemen, do you remember that I promised you an applause? Can I ask everybody to be a source of gravitational waves and give them their well-deserved applause? This is what we're going to do with the Einstein Telescope. Literally, we're going to build this machine one more time, but a lot bigger. 10 kilometers instead of 3 or 4 as our current detectors do. We're going to build it on the ground. So that means that all the seismics, people walking about, the earth shaking, are minimized on the way down. We're going to make it cold, because heat is also sort of disturbance, and we don't want that at all. We're going to make it vacuum, because we're going to sprinkle particles over my laser, they don't work as well anymore. And we have to get the best technologies out. If we do that, we're going to go from here, look at the right picture, these are current detections, right, to this. Remember, a second ago I mentioned that with the current detectors we measure about 100 gravitational waves every 10 years. The Einstein Telescope, if we can make it to work, will measure about 100 gravitational waves every single day. So we're going to get as much data as it now took us 10 years every single day. Now think about how many snapshots of the universe we're going to make, how fast that will go. We're going to really fill up our history book of the universe. And it's better than that still. How far can the Einstein Telescope look if all works well? All the way to the edge of the visible universe. So we're not just going to measure about 1 million times more gravitational waves, all the way until we cannot see anymore. Well, that's big science. Now, that machine I mentioned at the very beginning still has to be built. Where it's going to be built is up to the politicians. It's going to be in Europe someplace. There's 2 candidate sites left. One of them is in the beautiful island of Sardinia, Italy. And the other one happens to be the southern part of the Netherlands. Guess which one has my preference. But before the politicians make their decision, by the way, I should add that although, of course, at some point it can only be either in Italy or in the Netherlands, it will in all cases be a European project shared by Italy, Netherlands, Belgium, France, so on and so forth. So it's going to be a European project no matter where it will stand. But as we are waiting for the politicians to make up their minds, we can already build the technology that we're going to need. And that we have already done. We have a machine in my current home city of Maastricht that actually has the Einstein Telescope pre-built for us. It's called the ET Pathfinder, the Einstein Telescope Pathfinder. It's a small version of the Einstein Telescope, way too small to measure gravitational waves, I should say, but we have to get the technology right. We have to get better laser technology, we have to get better vacuum systems, our computers have to work a lot better, and we're not going to wait until 2035 before the big machine has been built. We're going to already create the technology now. So by the time the big machine is ready, we have everything waiting in the wings and get the measurements all done. So this is why we're highly supported by many countries in Europe, because, well, good technology is good for everybody. Better laser systems, good for industry. Better computer systems that can calculate 100 times, 1,000 times faster, good for everybody. So on and so forth. So let's recap. What does the Einstein Telescope give us as opportunities? Well, first of all, we're going to see about 1 million times more than we have seen so far. We will even see things that we probably don't even know exist. Every time that we as humans built a new machine and turned it on, there were things that we knew existed, we just see them a lot better, but there were always things that nobody knew existed. For instance, when people first built a microscope, they put a water droplet underneath. They saw little animals floating in it. Nobody knew that those existed. When Galileo made his actual first telescope and looked at Jupiter, he saw moons orbiting around Jupiter. Everybody thought everything moved around the Earth. It didn't. So on and so forth. Every time that we build a new machine, humankind, we're going to see things nobody knew existed. And at the same time, we're also going to have all this useful technology that hopefully directly goes back into society. And again, all of this is something that you don't have to be a mathematical wizard for. We can teach this to our 10 to 20-year-olds that are now in school. So, what do gravitational waves offer us? Well, for me and the other scientists, we're going to look at the universe in a way that we've never done before. For the technology and industry, we're going to have all kinds of new technologies that we're going to build together. Directly goes back into technology. And it would be very nice that if we're going to have the machine in Europe, we're going to have the center, so to say, of the universe. We're going to measure all these things that nobody's ever seen before. But now I'm going to go all the way back to the start of tonight. I think it's also an opportunity to make sure that our young generation also knows about this and that they know that they're welcome too, that we love their new input. If we're going to see new things about the universe that nobody's seen before, don't ask me because I think in the old way. We're going to need people who are going to look at this with a fresh mind. So we have a golden opportunity here to also make sure that young students are going to join us in this effort if they so want. Now, I know that this works because we actually opened our own Einstein Telescope Education Center where we do exactly that. So if you ever happen to be in the Netherlands, it's free of charge, free. We have 4 stories of beautiful gravitational wave experiments and exhibitions that we use to teach our children in secondary school. So, to wrap up, I think the Nobel Prize winner of 2040 is already among us. How do I know? Because everything that we spoke about today only used high school physics. The only thing I used was how does light work, what is light, what is mass. And that means it can be taught to high school students. Meaning that these people, or maybe somebody in the room, or in Europe, in the UK, is going to be very excited to see that they can study physics too, become part of this enterprise, and potentially even win the Nobel Prize in 2040. And with that, I thank you for your attention.